Hello, everyone. My name is Karol Duzinkiewicz. I'm a senior computer vision researcher at DAC.digital. And today I would like to tell you about a project I've been involved in for the last year and a half, namely building an in-the-wild gaze estimation solution for one of our external clients. Let's briefly go through today's agenda. First, I'm going to say a few words about myself and the team behind the project. Then I'll move to an overview of a problem we're trying to solve and present a proposed solution. The majority of the presentation, however, will be more of a story about overcoming various challenges that me and my team faced during our work. I'll close my presentation with some results that showcase where we are currently with our solution, and finally talk a little about the steps that are still ahead of us. A few words about myself. I currently hold a senior computer vision researcher role at DAC.digital, which I've joined about 2 years ago. I've worked for tech companies my entire career, starting from a small startup right after graduating, up to working for the Intel Corporation for the majority of my professional career so far. My areas of expertise include computer vision and speech processing, both using legacy methods and also deep learning approach. I would also like to recognize my engineering team at DAC.digital, namely Jan, Andrzej, Cezary, and Artur, who also contributed to today's presentation through their work. Let's start with a definition of the problem. Gaze estimation is generally a way to tell where a person is looking. We either try to estimate a gaze vector in 3D space or a point of gaze on some flat surface, like a screen of a device. There are various ways to approach this problem. From the algorithmic perspective, there are two major groups of solutions: eye model approach and appearance-based approach. The eye model approach has a longer history. It generally tries to model eye movement with some mathematical equations, leveraging knowledge about human anatomy. Appearance-based approach, on the other hand, analyzes image of the entire face or eye crop, usually with a deep neural network, to extract information about the gaze. When it comes to input signal, there are various options available. Some methods use an external hardware mounted above or below a screen. Other methods rely on dedicated eyewear equipped with IR and RGB cameras. Finally, some approaches like ours use cameras already built in mobile devices or laptops. Here you can see a few examples of dedicated gaze estimation hardware and eyewear. On the left side, it's a Tobii eye tracker device, an external camera you place under your display. Another example on the right is Pupil Labs Neon eyewear equipped with really small IR cameras pointing at every eyeball. Those devices are accurate, but can be a little cumbersome in use, depending on the use case. They are usually based on IR technology, so it may be impossible to use them outside in strong sunlight. They are also relatively expensive, starting from around $300 up to several thousands of dollars. Our goal was to build an appearance-based gaze estimation solution that would work in the wild. By in the wild, we understand a system that will work on virtually any device with a built-in user-facing camera and in a wide range of lighting conditions. Possible use cases for this type of system include attention tracking and analysis of content consumption on mobile devices. On the right side, you can see an overview of the solution proposed by us. It consists of a gaze estimation SDK, a gaze estimation web service, and a gaze estimation processing pipeline. It also leverages cloud storage functionality. It's AI-based, meaning the gaze estimation model is a deep neural network. It's cloud-based, meaning videos captured on target devices are processed offline to acquire results that can be later revisited and analyzed with regards to displayed content, for example. The web service covers triggering file transfer and processing operations, and the processing pipeline running on backend does all the number crunching to output POG estimations on a per frame basis. Here you can see a list of main technologies used to build our solution. On the front end, we have used TypeScript, MediaPipe, and OpenCV. On the back end, we have used Python and PyTorch for building deep neural network models, OpenCV and MediaPipe to do some computer vision processing, Fast API to build the service, Docker to deployment, and AWS for cloud storage. The most important part of the entire solution is the case estimation processing pipeline. It works on a frame-by-frame basis. When it receives a new frame from a video, it starts with normalizing the image based on head-pose estimation. Normalized image frame is passed to the gaze vector estimator. In order to go from normalized gaze vector to an actual point of gaze in screen coordinate system, we need to perform some additional calculations using camera intrinsics and device's physical parameters. Some of the data necessary to perform these calculations are easy to acquire if you have the device at hand. Camera intrinsics can be acquired during a camera calibration procedure using some predefined calibration targets, while device's physical parameters can be obtained by simply measuring the device. The real challenge is to obtain all this data in the wild, so not having the device at hand. I will talk a little more about this later on in the presentation. Let me now talk more about the challenges that we have faced on our journey. I will go through topics related to data collection, data review, training gaze estimation model, phone parameters extraction, a camera auto calibration, and finally end-to-end pipeline calibration. Let's start with data collection. As you may know, training a deep neural network in general requires a lot of data. There are publicly available data sets for our use case. I have listed two examples here, MP phase gaze and gaze capture. Unfortunately, the license for those data sets prohibits use in commercial products, and this is what we're trying to build here. Below, you can see an example of frames from gaze capture datasets, so you know what kind of data we're dealing with. In order to collect proprietary data from many different devices and many different people, we have developed a web app and used it in a crowdsourcing platform. We have been able to successfully collect video and metadata from more than 550 unique test subjects and more than 300 different mobile phones. On the right side, you can see our data collecting app in action. First, the user is asked to grant access and necessary permission and configure the app to work in full screen mode. Then the user position within the camera field of view is verified, and when everything is okay, the user is exposed to a sequence of random target locations on which the user is supposed to focus the gaze. The recording from the built-in user-facing camera is collected and sent to cloud storage. We don't have much control over who uses the app, so as you can see from the charts, the collected dataset is somewhat biased towards men of white ethnicity, but we are currently working on making that dataset more balanced. Unfortunately, not all test subjects did their job right. Below you can see examples of such situations. Some people were not focusing on the task. Some recorded themselves in a very dark environment. Yeah, the second picture is actually a man smoking a cigarette in complete darkness. Some people were not in the camera field of view, and some videos were just very blurry. By the way, I needed to anonymize the images since we're not permitted to publicly share collected images and only allowed to use them for training and evaluation purposes. Since the amount of data was so big, we needed to come up with an automatic video review framework to quickly mark outliers in the dataset to exclude them from the training procedure. So every video is globally analyzed to estimate age, gender, and ethnicity. Every frame in every collected video is analyzed to calculate various metrics like level of blurriness, brightness of face region, correct face location, overall face visibility, face-to-screen area ratio, iris visibility, and even eyewear detection. All the videos have been also manually reviewed by a group of testers to apply some general quality labels. And all analyzed frames are stored on AWS S3 storage, and the related metadata are put into a non-relational database to enable easy filtering for dataset creation purposes. We have used various approaches to detect different issues with the collected videos. Here you can see a few examples. Some of the methods leverage legacy computer vision algorithms, while others use deep learning model approach. For face brightness detection, we have used YOLO V8 for foreground segmentation and MediaPipe for face detection. For blurriness detection, we have used fast Fourier transform combined with Haar wavelet transform combined with Laplacian to create a weighted blurriness score. For face visibility detection, we have simply used MediaPipe and its face keep-on detection feature. And for eyewear detection, we have used a custom trained YOLO V8 to detect who wears glasses and who doesn't. The gaze estimation model is basically a convolutional deep neural network that outputs estimated normalized gaze vector as yaw and pitch angles. Unfortunately, my contract doesn't allow me to share more details about the architecture at this point. For training the gaze estimator model, we are using the proprietary data collected using crowdsourcing approach. Before feeding into the training procedure, every frame is normalized, meaning it's warped and cropped to simulate a view from a camera directly in front of a human face at a given distance. Image normalization makes the gaze estimation task easier for the model. Below, you can see how frame normalization works in practice. No matter how the head is positioned in the actual camera field of view, frame normalization transforms that frame so the tip of the nose is directly in the middle of the normalized frame, and eye centers are aligned to lay on the line that is parallel to top image side. The next challenge was to extract phone parameters like screen size, camera location, and camera matrix for a phone on which the video has been captured. This information is critical in order to convert yaw and pitch angles for normalized frame into an actual point of gaze in millimeters in the screen coordinate system. Unfortunately, there is no easy way to reliably extract this information from the device itself. We have developed a framework to estimate physical phone characteristics based on just a phone code name that we can extract from a web app level. Thanks to a third-party phone database we have acquired, which includes phone photos and other metadata, we are now able to generate a device configuration file necessary for the calculations. On the right, you can see an example of information we're extracting. So you can see that we aim for extracting the width and the height of the screen, and also the offset between the top left corner of the screen and the camera. Thanks to a custom-trained deep neural network, we are able to locate the screen and the camera in phone images. Here you can see a few examples of how this algorithm works for various devices. Another piece of the puzzle we're missing when operating in the wild are the camera intrinsics, namely the camera matrix. It's important for accurate head pose calculations, among other things. Typically, camera matrix is calculated during a camera calibration procedure, which involves using a calibration target and recording its image representation in various locations within the camera field of view. So you basically move that calibration target in front of the camera. Below you can see the examples of different calibration targets. The procedure is very accurate when done right, but is very problematic for in the wild use case because we can't simply expect that every user would have this type of calibration target at hand. That's why we came up with a different approach. We can use phase landmarks found in a sequence of images to estimate camera matrix. Our solution is based on the paper provided under the link. The procedure requires the user to move the head in front of the camera for a few seconds. Phase key points are located in every frame and fed into the deep neural network, which estimates the camera matrix. Even though we try to estimate phone's physical parameters and camera matrix, the unprocessed output from the gaze estimation model is not very accurate. The trend is there, but usually some scaling of the POG location is applied due to various errors at different stages of the pipeline. That's why a user-specific and device-specific calibration procedure is necessary to increase the accuracy. The solution that we are proposing is currently patent pending. First, the user is exposed to a sequence of target locations on which he or she is supposed to focus the gaze, similar as in the data collection procedure. Then we use support vector regression model to create a mapping to go from a raw unprocessed POG locations to fine-tuned ones based on the location of ground truth. Once this mapping function is calculated, it can be used during normal operation of the pipeline when the user is exposed to various content and no ground truth is known. Below, you can see the result of end-to-end pipeline calibration. On the left is the raw unprocessed output from the gaze estimation model. On the right, you can see how those inaccurate POG locations have been transformed to much more accurate. Finally, I want to present some results of how our solution works in practice. On the left side, you can see an example of gaze estimation pipeline operation. You can see both the source video frames and the normalized frames in the top right corner of the video frame. To the right, there is a render of ground truth POG locations in blue, meaning the target location on which the user was supposed to look at. The red cross illustrates the output from the gaze estimation pipeline. On the right side, you can see some numerical results on our proprietary evaluation dataset of 50 randomly selected test subjects. You can see that our solution works best for people that don't wear glasses due to frequent reflections that appear on glossy surface of the lenses. On average, we get around 17 millimeters accuracy across all evaluated test subjects. This solution may not be as accurate as hardware-based solutions, but it's good enough for our use case, which is overall attention tracking and content consumption analysis. It's worth noting that we are currently supporting both portrait and landscape mode of operation. Here you can see two examples of how that works. I would like to close my presentation with a short list of next steps. First of all, we're constantly collecting more data for training and testing purposes. However, we still have less data collected than gaze capture dataset, for example. We are also going to experiment with different end-to-end pipeline calibration patterns beyond just random target locations. We also have a few more patent submissions on the way. And that's it for today's presentation. If you have any questions, I will be happy to answer them. I also encourage you to rate this presentation using the link provided on the next slide. Thank you all for listening, and see you soon. Take care and bye-bye.